All right, starting chapter 12, we're starting off kind of slow with three-dimensional figures. We're going to be getting into finding surface area and volume of these figures, but first we're going to be learning about their different components. Okay, we refer to these figures as polyhedrons or polyhedras, the plural version. They're solids with all flat faces that enclose a single region of space. So some of the different examples that you might see are cubes, cones, pyramids, prisms, those types of things. All right, so a face, you need to know what a face is. The face is the amount of space figure are the flat sides of the figure. So if you're to draw a cube, okay, all the flat parts would be a face. So right here in the front, I'm going to shade that. That would be considered to be a face. This side over here, underneath, behind, on top, over on this side. This particular prism has 6 different faces to it. Okay, now then an edge, the edges are the line set. So I'm going to draw another prism again. I was trying to draw a cube, but it didn't turn out to look like one. So we'll just call it a prism. Okay, these are your edges right here. This is an edge where 2 faces meet. This is an edge. This is an edge. This is an edge. So everywhere you see a line is an edge. There would be 4 on top, 4 on bottom, and 4 that were vertical going around it. So that would give you 12 edges altogether. A vertex. The vertices are the corners or the points of the intersection of 3 wedges. Okay, so it's where of 3 edges. So it's where 3 different faces tend to meet up. So let's go ahead and draw the prism again. Okay, and this would be a vertex right here. And right here. So all of these corners that you see, these are your vertices. And of course there's one back there as well. So there would be 1, 2, 3, 4, 5, 6, 7, 8 vertices on this particular prism. All right, a base. Now, this is important when it comes to using your formulas. Later on in the chapter, the bases are the 2 ends of a prism or cylinder, or it is the bottom of a pyramid or cone. Okay, so we're going to start off drawing a cone. And it's got the circular bottom. This is considered the base right here. Now, I'm going to draw a prism, a long rectangular prism. Okay. Now, my bases on this one would be here and here. These would be considered the base. Okay. Doesn't matter that it's not sitting on its base. It's like the distance between the 2 ends is basically what you're looking at when you're talking about a base. On a prism, however, these could be, you could use this bottom part as a base as well. But usually the long rectangular parts of the prism are between the 2 end points, the 2 bases. So that's why I've colored the ends such as these. This could be argued though, and you could still very easily solve the formulas and problems using this part as a base and this part as a base up top. Okay. A pyramid. A pyramid is a polyhedron that has all faces except one intersecting at one point. So we've got, we'll make it a square base. Okay, so we've got what we call a square pyramid. So all of the faces, 1, 2, 3, and the one in the back is 4, come to a point except for one, and that would be considered the base down there. This is a pyramid. A cone is not. It is a circular bottom, and it is separate from a pyramid, even though it has a point. A cone is not considered to be a polyhedron because it is rounded. And so this part right here doesn't have a flat face to it. All of these have flat faces, every single side, whereas this one, the cone part here, is not flat. So that is not considered a polyhedron. All right, a prism. A prism is a polyhedron with two congruent faces that are polygons contained in parallel planes. Okay, your prisms are named by their bases. So if I were to make a triangular prism, my bases would be triangles, and I would just connect them as such. Okay, so this would be a triangular prism. This could be a rectangular prism. I'll draw one elongated. You can draw pentagonal prisms so that there's a pentagon at the end of each rectangular side. It's just whatever the shape of that particular face is, that's the type of prism that it is. All right, now there's a little formula here. It's not a hard formula. It's called Euler's theorem, and this is something you can do to fit the number of faces, vertices, and edges that there are in any type of polyhedron. F is going to represent faces, V represents the vertices, the corners, E represents the edges, the lines where the sides faces meet. Okay, this is the formula. The number of faces plus the number of vertices is equal to the number of edges plus 2. So let's take a look at this one right here. Okay, we have the number of faces, 1, 2, and then there's 4 going around it. So there's 6 faces, 6 F's, plus vertices, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 vertices, is equal to the number of edges. 1, 2, 3, 4, down at the bottom, 5, 6, 7, 8, and going around 9, 10, 11, 12. So 12 edges plus 2. And if you look, 6 plus 8 is 14, and 12 plus 2 is 14 as well. So that's just kind of a little problem. So if you didn't have a picture of something, you could kind of figure this out by using that little formula. Okay, now the rest of these are going to be used as homework where you're practicing. You're naming these figures. You're counting up the number of faces, vertices, and edges that they have. These names are in your book, and I'm going to be having you look them up. Same thing on this next page. Okay, you've got some more polyhedrons that you'll be referring to. Now then, this next section, you've seen tons of problems on TAKS before. These are isometric pictures, and those are basically your three-dimensional pictures that are on so that you can see them from different angles. Okay, these are some practice problems that you're going to use, and you're going to count up how many cubes there are, how many faces you see in your top view, side views, etc. This is a good practice on TAKS. Down here at the bottom, okay, we've got these different views of these isometric drawings. However, these are flat. We don't see them at an angle. All right, what you're going to do is figure out how many cubes are being used by looking at these different views. The top, every time you see a dark line like this, that means there's a break. So there's a difference in height or depth. Okay, one side's taller than the other, or one side comes in closer to you than the other. All right, the next page, what we're looking. You still have more practice with that. Part D, you're going to figure out where the missing letter goes in the word cube, because when you fold this up, you should have the letters spell out cube, and they should be facing the correct direction, going around in order. So in this one, you're missing the letter B. You've got to figure out which square the letter B would be written in, so that when you folded the when you fold up this template, that it would spell out the word cube. And you're going to be doing that for each of those. Okay. Then down here is matching your three-dimensional figures with its net. A net is a flattened drawing of a three-dimensional figure. This is huge on tax. You sometimes have these that you have to measure to find surface area or volume of, and you're going to be figuring out what these figures look like if they were cut open and laid out flattened. Okay. And part F, you're going to name the solids that are formed from each of these figures, and the name of the solids come over here. Again, these are all in your book, and I want you to be looking these up so that you can practice looking up and identifying information. And then identifying these solids, naming them, and then also here, label the remaining vertices of the net below. So here's what the figure looks like when it's folded up. Now if we were to cut it and lay it out flat, we've got some of the angles here for the different corners of vertices. You're going to put the remainder of the letters. So every single one of these letters should have a spot. And then last but not least, part I, find the surface area of the prism by the sum of each rectangle or triangle in the net. So instead of using a surface area formula, you're going to mark the different dimensions on each of the rectangles, find the area of each rectangle, and then add it together for total surface area. And that will be it.